Good morning. Welcome to Microsoft Reactor. We're going to be talking to you today about a type of machine learning that involves collecting data and then trying to make predictions from it. It's a type of machine learning that we would call supervised learning, and it's a very interesting example that I think you'll enjoy, dealing with the interrelationship between, say, your mobile devices and what you're doing at the time. We've got a really interesting reality to our world these days, in that the sensors around us, the sensors that we carry on our bodies, the sensors that we install in our homes for Internet of Things devices, gives us the capacity to collect data about our daily lives, and that can be interesting to try to learn from. My name is Brian Slatton. I'm coming to you from Northern California, so it is very early in the morning here, and I hope I sound awake, but I hope you're doing well, and I'm glad that you're able to join us today. So there's a lot that goes into an activity like this, and we've broken up the introduction to the ideas throughout the series of workshops and online events. So if there's something that you don't understand, feel free to ask in the chat room, and Emma will relay some of those questions to me. But I may also encourage you to check out some of the other courses, some of the other videos and things that are available, attend some of the other sessions, because there's only so much we can cover in the time period that we have, but I'll try to do whatever I can to at least point you in the right direction. So we are going to be using a code sample that is available to you through Microsoft's GitHub repository. And if you go to github.com/Microsoft/reactors with a capital R, you will get to the base of all of these workshops. Tremendous amount of resources here for you to available to you to just download and play with, but I encourage you to take a look at them. We're going to head down into the directory called Workshop Resources. In Workshop Resources, there's one called Data Science and Machine Learning, and within that one, there's a directory called Data Science 2, and in that one, there's a project called the Human Behavior Project. So again, through all of these activities, there are several topics that are covered in various levels of detail, and so I encourage you to give it a shot. You can check out the whole repository, and it'll be available to you. But we're going to be using Microsoft Visual Code, which has, with the Python extension, the ability to run Jupyter Notebooks directly within the environment. Normally with Jupyter Notebooks, you would need to have a Python environment that's configured to give you all the machine learning libraries that we're going to talk about, like NumPy and Pandas and Jupyter Notebooks itself, and it will have to run a separate server, because you usually run the Jupyter Notebooks in a browser, and browsers are not directly able to run Python these days. With WebAssembly, that's changing, but for our purposes, just to avoid the need to be running a separate server, and to take advantage of the nice code formatting and completion and everything, we're going to use Visual Studio Code. So in order to follow along, you can check out the repository, and then in Visual Code, you'll have to install the Python extension. So if you just search for, where is it? Yes, here it is. The Python extension from Microsoft, that will generally give you what you need. As long as you have it installed, it will find the Python instance, and then we'll be able to run within this tool. All right, so we are going to talk about algorithms that help us classify data elements against some kind of known output. And usually with a classification exercise, the output will be something like, oh, you're going to be this kind of customer or this kind of sales opportunity. And the intuition that we get is from collecting the information from historical data. And so the idea is if we've seen customers of a certain type, maybe they're more budget oriented, maybe they're more luxury oriented. If there are elements of the customer's data sets, how they spend their time, how they spend their money, whatever you've collected about them in the past, you can hopefully start to build a picture of what other customers are also like that. And that's useful then because, if you have a luxury oriented customer, you're not going to want to try to sell them on a budget oriented experience, right? You're going to want to focus in on, oh, this is a lovely restaurant. This is a luxurious hotel. But if you have a more budget-oriented customer, you're not going to want to target them towards the expensive luxury experiences. You're going to want them to be able to get some kind of money off, for a discount, checking in early, something like that. And because obviously, if you pick the wrong approach with your customers, they're going to think you don't really understand them, and that would be a bad customer experience. So there's usually some kind of outcome that has been provided to us, and that is called the label, the output, the thing that you're trying to predict. And somebody has to go to the trouble of doing that. And so that's one of the more tricky parts about supervised learning is not just collecting the data in the first place, but having the labeled outputs and having those labeled outputs be valid and useful. And so very often, even though you can deal with any kind of data, you're going to want some kind of domain expertise to evaluate the labels that have been provided and make sure that the data that you're trying to learn from is accurate, consistent, that the process of collecting the data hasn't skewed it in some way. So we're not going to really have that problem because the activities that we're going to try to predict are based on the acceleration, gyroscopes, and whatnot within a cell phone. And the activities that we're going to try to predict are whether somebody is walking upstairs, walking downstairs, if they're sitting, standing, or lying down. And you've probably experienced something like this. If you have a Fitbit or a mobile phone with some kind of tracking activity, they have built models based on studies of humans and the experience of the forces that affect the acceleration sensors in the phones, and those are going to be correlated with the particular activity. So in this particular case, the data set we're going to use, which is in a directory below the directory we're in, has already been collected. It's already been labeled. And so this is a data set that involves a series of readings for 30 volunteers. They're adults in the age range between 19 and 48. And the people in the study would have basically just gone about their day, walking, as you said, going on the stairs, sitting down. And the embedded accelerometers will capture the directions, the angular rotation of the gyroscopes, etc., at a rate of 50 hertz. So this is collecting samples, and the activities will be tracked and probably verified by the volunteers themselves. So that's where the data is coming from, right? They are indicating what they were doing at the time, and therefore we can try to build a model from that. Now it's interesting, as framed, we talked about the age of the volunteers, and whether somebody is 22 or 23 or 33 or 34 probably isn't as important as whether they are a child, a teenager, or an adult, in part because the physiology will be different, right? We'll be talking about people's bodies and center of gravity, and those sorts of things will be different if the volunteers are adults versus children. Obviously, the behavior is going to be very different, right? Children might get up a lot and run around, particularly if they have too much sugar or something. So the point here is we have to be aware of where the data comes from, and we have to be aware of the variation in the data, because if we try to train off of adults and then predict off of children, that's not likely to achieve good results. And so one of the first places that these things can go wrong is in the data collection process. So here we should be okay. We have a fairly consistent data set. The range of ages is such that we're talking about mobile active adults. If the adults had some kind of physical ailment, or they couldn't walk the same way, or they had trouble standing up, obviously that would impact the quality of the results as well. So the main point here is we're using supervised learning processes that requires knowing the outputs, knowing the labels, having those labels be validated and consistent, and then having it be relevant to the audience that we're trying to make predictions of. So we're not trying to predict the behavior of the volunteers. We're trying to predict the behavior of future adults in without the labels, right, by monitoring their own activity. So if somebody has one of these phones on and we have this historical data that we've learned from, then the models that we use could help us indicate whether the person that we're trying to make predictions off of is doing similar sorts of activities. And so that process of training the model and then applying it to a new population does require that the new population has roughly the same characteristics, roughly the same shape, roughly the same values. And but if those things are consistent and we have done a good job in our training process, then we would say that the model generalizes to data that we haven't seen before. And so that's one of the things that we want to make sure, that we're not just simply memorizing the details about the individuals that were part of the study, but that they actually are finding some kind of signal in the data that generalizes to behavior of even people that weren't part of the study. And if we find that that's not the case, then we might have a problem with our training process, and we might be in what's called an overfitting situation, where if you just memorize all the details, this, volunteer 0 at this time was standing when the numbers looked like this, then that's not as interesting or useful, right? Because that volunteer is not going to necessarily be in the general population we're trying to make predictions off in the future. Therefore, all the effort to memorize those details won't help us in that case. I like to say in my classes, it's a little bit like if a student finds the answer sheet to a test, he will memorize the answers and look like he did a very good job. But the reality is he hasn't actually learned anything. And if presented with a different test or different questions, you'd be able to tell pretty quickly. So with machine learning, the way that we manage that is to use a split in our data. We take our training data and we split it so that some amount of the data is used for training purposes and some amount of the data is used for testing purposes. And that's going to give us the ability to detect. If we do well with the training data and we do well with the test data, then we have learned something, right? The patterns that we've identified are generalizing well to data that we haven't seen before. That's the whole purpose of the test data, is it wasn't used as part of the training data. So we'll see a couple of examples along the way on how to handle that. So for each of the elements, or for each record in the data set, we have the triaxial acceleration from the accelerometer. This is the total acceleration for the body's movement. We have the triaxial angular velocity of the gyroscopes that catches rotation movements, and then a 561 feature vector with time and frequency domain variables. Again, I'm not going to go into the details of this too much. In general, you would have to understand the data, or at least somebody involved in the project would have to understand the data. But what we're doing is we're capturing the elements of motion, and we're decomposing them into a series of time-stamped measurements, and then we have the activity label that's associated with that. And as I said, the general activity that we're going to try to pursue now is to train off of the data to find some kind of connection between those. So the first thing that we're going to do is we're going to load in some of the libraries that we're going to need. And we're going to be using a collection of libraries. One is called NumPy, and it is a numerics library that makes Python useful for this kind of calculation. Under normal circumstances, Python, because of its dynamic nature, has a lot of overhead around the objects that are created. So a Python variable can hold any value, but the values that you associate with it have to be somewhat self-describing. So there's a lot of metadata around each Python object. And so an individual integer or an individual floating point number, actually comparative to a language like C or C++, has a lot of memory that has to be allocated, initialized, configured, and that's just a lot of overhead. The process of resolving those numbers is time-consuming as well, and compared to a language like C or C++. So what NumPy does is it allows Python to store the data down in the C implementation. This version of Python is based on a C engine. And so it's able to more efficiently represent the data. It's able to more efficiently access the data. And that simple act makes the numerics much more reasonable, right, for this kind of calculation. So NumPy makes Python numerics much faster, but it doesn't change the semantics of the language or anything. So it's easy to take regular Python lists and objects and convert them into this more efficient form. But we're going to be reading some data in from a spreadsheet, a series of spreadsheets, using another library called Pandas. And so if you've dealt at all with R, the programming language, or if you've dealt at all with Spark and its data structures, you may have come across the term data frame. Pandas is going to give us a data frame interface to our data. And you can think of a data frame as a little bit like a spreadsheet. It's a programmatic spreadsheet that allows us to access the columns of the data, the rows of the data, and it's just an easy way for us to think about it. So Pandas is the library that's going to read the data in from the spreadsheet, convert it to a data frame, and then throughout the remainder of the session, I'll show you a series of features that Pandas brings for us. We're going to be using two visualization libraries. One is called matplotlib, and the combination of NumPy, Pandas, and matplotlib is very common for data science and data analytics within Python. Seaborn builds on top of matplotlib, and it's what we would refer to as kind of an opinionated framework. That just simply means there's a particular way of using it, and by default, it does a lot for you. And that way you have to write less code to achieve good results. The Ruby on Rails framework is an example of an opinionated framework. If you like the way Rails does stuff, you don't actually have to do that much because a lot of it is inherited behavior. So Seaborn allows you to create very nice looking visualizations without a lot of low level effort. So we'll see an example of using Seaborn a little bit later. And then the final library that we're going to introduce is called Scikit-Learn, and this is where all the machine learning is going to happen. It is a very nicely designed, very user-friendly library, and it comes with not just the algorithms for learning, it comes with sample data sets. We're not going to be using them. We're going to be using a different data set, but it comes with sample data sets, tools for evaluating how models are doing, the ability to manipulate the data in some ways, and then we're going to be using a series of classification tools. One is called Logistic Regression, and even though it's called regression, and that means something else usually in machine learning, where you're predicting a numerical output, this is a classifier, and it's usually used for simple kind of binary classification purposes. But in our case, we're going to be using it to make predictions amongst several labels. And then the other type of classifier we're going to use is called a random forest classifier. And that's a different kind of classifier. One of the neat things about Scikit-Learn is that the APIs are very consistent. And so all of the supervised learning activities look the same way. Most of the classification tools look the same way. And that makes it easy to swap one out for another. So where one classifier might do well with one data set, a different one might do better with a different data set. And you as the data scientist can just switch between them and see, evaluate them independently. So we're going to look at a couple of different variations of the classification models and evaluate the results. So in essence, what we're going to do here is we're going to import all of these as aliases so that we can access the code further down. You'll notice if you are new to Jupyter Notebooks that when I push the play button here, the character in between the square brackets becomes an asterisk briefly. That tells you that the engine is running, and when it's done, it gives you a numeric reading to indicate that the cell is finished. So Jupyter Notebooks, again, just if you're new to this, are generally ways of telling data science stories. You wouldn't necessarily take them into production or anything, but you can check them into Git. Obviously, we check this out of Git. And as long as you have an environment that interprets the Jupyter Notebooks, then there's no really other installation or tools that you have to deal with. So it's a great way of mixing a narrative with the code that you're dealing with. So as you can see, we're going along and we have documentation cells that explain what's happening at each level, and then the actual code levels. It is a stateful system, so once you introduce a variable, it will be available in additional cells. If you happen to accidentally skip a step, so the next one for us is to read in the data. If I skipped this step and just tried to run the next cell, notice that assumes that the data has been read in. You may end up seeing some kind of error. Now I've run this multiple times before, so I didn't see that error, but you might see something down here. So just if you happen to see those kinds of errors, make sure that you have run the right cells. Okay, so in this case, we're going to load in the data. It's been pre-split for us. So 70% of the data is considered training data, and 30% of the data is considered test data. They will have the same structure. They will have the same features. They will have the same type of labeled outputs, but they're just broken up. And again, the reason for that is to keep the test data separate, so it's not part of the training process. That way we can give the training activity the inputs, which represent the features that we're looking at, the output, which represents the activity we're trying to learn how to predict. And then we'll build a model from that. We'll then take the test data inputs, plug them into the model, and make predictions, and then compare them to the test outputs. So we know whether the test characteristics suggest whether the volunteer was standing or sitting or lying down, and our model will see how well it predicts it. So this step is going to read both of these data sets in using Pandas. So PDs are an alias for Pandas. We're going to call the read CSV function, and that's going to read the two CSV comma-separated value files out of the data directory, which is below us in the Git repo. So once I execute this, as you saw, we have two variables. One is a data frame called train, and one is a data frame called test. And usually what you do with a data frame once you read it in is to call a function like head or info, which tells you something about the data, and it also shows you the columns. Now, because we have quite a few features here, it doesn't fit into like a normal grid, but usually if you have like 5, 10, 15 features, they will look more like a spreadsheet. But what you see is here we have the first 5 rows. By default, head shows you the first 5 rows. If you give it a parameter like 10 or 20, it'll show you that many rows instead. But we're okay with the defaults. So we have the first 5 rows for each of the features that we have captured. So we have the body acceleration average x, body acceleration average y, body acceleration average z. So we have 3 dimensions, and it's on average what is the movement in each of those dimensions. And then we have the standard deviation measured of the x elements as well. So there's been a fair amount of pre-processing to the data, and we can see that it basically ranges between -1 and 1 in terms of the values. And we'll come back to why that's interesting in just a minute. The other thing we want to make sure is that our test data looks quite a bit like our training data as well. So we see, again, the same features, the same basic range of values in there. That's important because, again, if you try to train off of data that looks one way and test off of data that looks another way, there doesn't have to be the same values, but they can't be completely different, right? If one is units in Fahrenheit and the other is units in Celsius, it's not going to work out. If you're training based on like geography, you can't train generally on, say, European data sets and then try to generalize to maybe South American data sets, because climate and geography and a bunch of things would be different. So the fact that we haven't seen the data yet is okay, that we're trying to predict, but it has to look kind of like what we are trained off of. Otherwise, the results are not going to be good. And that's why you have to have domain expertise involved. It doesn't have to necessarily be you, but somebody involved in your project has to evaluate whether the data that you're trying to predict is coherent and consistent with the data that you are training off of. The other thing I'm going to point out here is the final feature, the final column in our data frame is the activity. And notice this is qualitatively different in that it's categorical data, not numerical data, but this is the labeled output. This is the thing that we're trying to learn. So we can see in this case, with these values that we've seen so far, the 0th row, which represents one sample, in that case, the volunteer was standing. Okay, so we've gone through and we've familiarized ourselves a little bit with the training and the test data. It looks fairly consistent. The next thing we want to do is to look for oddities in the data. So that could be missing data, that could be outliers. If we had somebody who was exceptionally active or like jumped up rather than just standing up normally, the numbers might not look the same as other ones. And that's not necessarily a problem. We just want to be aware of it, because if there are a lot of outliers, they may or may not represent the typical population. So if you're trying to predict how tall somebody is, and you had, maybe a basketball player or Peter Dinklage from Game of Thrones, right? Those would represent outliers compared to the normal height ranges you would expect from, typical adults. And so again, they would be part of the data set. That's not a problem, but you want to know that they're there in case you do need to manipulate the data somehow. Other things you want to look for are missing data. Yep.
Sorry to interrupt. We've just had a comment through from an attendee who's with us. So Jeff has written, I get runtime error. The current NumPy installation, and then the link, fails to pass a sanity check due to a bug in the Windows runtime. See this issue for more information, and then another link.
Unfortunately, I am not able to respond to that at the moment. I would be happy to try to help afterwards, but that sounds like an installation issue. Generally, I would make sure that there's not some sort of like known registered issue with VS Code or the version of Windows you're dealing with. So I apologize about that, but I'm not able to. It just sounds like an installation incompatibility of some sort. So if there are multiple Python installations available, you can usually click on down here on the lower left-hand corner to select which interpreter you want. So I would say maybe try and see if there's another interpreter that's available. You'll probably want to have a Python 3 interpreter if that's not what you're using. Python 2 has basically been end-of-lined and deprecated. So I hope that's useful. But unfortunately, not being able to see your screen or anything, and not having Windows to test it on, it'll be a little bit difficult for me to directly answer that question. So feel free to reach out afterwards if you're still having those issues. We'll make sure that you have my contact information, and I'll see if I can help you there. All right. So again, we want to look for outliers. We want to look for missing data values, because again, the quality of the data is going to impact the quality of the results. And if there's something about the collection process that is skewing the data in a particular way, then that has to be addressed before you can hopefully do anything useful with the results. So the first thing we're going to check to see if there's any null data. And the data frame has a method called isNull. And in essence, this is just going to go through and say, are there any null values for any of the cells, in any of the columns, in any of the rows? And fortunately for us, we'll see that the answer is false. If there were, then you would have to consider what to do. If it's just a couple of missing rows, usually you would just drop them, because it's not like you could go through and collect the new data necessarily, right? This is a study of some sort. Other options would be to fill in the missing values, and you can usually fill them in with maybe the average value for everyone else, or the most common value of something. There's no right answer on how you address that. This is part of the art of data science, is understanding the implications of missing data and how you address it. But fortunately for our purposes, we don't have to immediately worry about that. The next thing that we're going to do is to look at the nature of the data. So the info function tells us a little bit more. It's a Pandas data frame. There are 7,351 entries, so that's the number of rows. We have 563 columns, so that's quite a lot of data to try to train off of. And usually, if you have that much data, then that many features, you're going to require tremendous more amounts of data to justify all those features. This is what we refer to as the cursive dimensionality. You may think that you want more and more and more details about each of your samples, but the reality is a lot of those features are not going to be strongly correlated with the output. And you can imagine if there is only, some samples that have those particular values, then that will end up seeming a lot more important to some model training processes than it should be. And that's where we get into the trouble of overfitting, because I'm just memorizing the individual details and the differences between them. So one of the things that we're going to do is we're going to try to suppress the less important features using a technique called regularization. And so we'll talk about that in a moment. So we have quite a few columns, but we can see that they're almost all floating point numbers, which we saw. There's one integer and one object. And the integer is the identifier for the subject. So which individual subject's readings are these? Generally, you do not want that kind of identification in the data set. So we're going to end up dropping that column. And then the object column is the category column, right? This is the one that says whether you're standing or sitting or lying down. And that's the thing that we're going to try to learn. So again, we're just getting familiar with the data set. We've seen that it takes up about 31 megabytes of memory. Pandas obviously is reading stuff into memory. So there's an upper limit to how much data you can deal with here directly. But I've frequently loaded data sets that have 1 million or more rows in them on even just sort of typical notebooks. So it's, your definition of big data may be different than somebody else's. I would not consider 1 million rows big data. Billions of rows, that's big data in my book. So fortunately, the test data looks roughly the same, 563 entries, 561 floating point numbers, the same subject identifier, and the labeled output is there. We also see that we're split up between 7,000 to roughly 3,000, so that comports with our understanding that the data is roughly 70-30 split. The actual numbers there don't really matter. It could be 80-20, it could be 75-25. It's just a question of, you want enough variance in the data to find patterns and be reflective of the populations that you're training off of, but not, we want sufficient data to test off of as well. So the first thing that we're going to do is we're going to drop the data for the column of subject, and the Pandas data frame drop method gives us that ability. So if you highlight or hover over this, you can see this is a link to the documentation. There's also built-in documentation on some of these things. You can call the help function, and there's built-in support within VS Code as well. So we're going to drop the subject column. Axis 1 just means it's one of the columns, not one of the rows. Axis 0 is the rows. Axis 1 are the columns. And the reason that's important is because columns are really just labeled sets of values, and rows are labeled sets of values. So we just need to tell Pandas, are we dropping a row or are we dropping a column? So in this case, we're dropping a row with the index name of subject. Normally, this kind of modification in Pandas doesn't change the data. It returns a view of the data. But in this case, we're telling it to do it in place. So we're actually going to literally drop the data in our data frame, and it won't be there anymore. We obviously need to do that for the test data as well. When you have the test and the training data as two separate data frames, generally whatever you do to the training data set, you're also going to want to do to the test data set in terms of manipulation. Other times you'll just read all the data into a single data frame, and you'll pull out rows as the test data set in different scenarios. But because it's pre-split for us, we have two separate data frames. So now if we rerun the head, we'll see that the subject is no longer there, and the columns, if we turn the column index into a list, we can see that we do not in fact have the subject column in there anymore. So you also see the names of all the individual features, which, as we said, we have quite a few of them. All right, the next thing that we're going to want to do is we're going to want to look at the types of the data, and the data types reference gives us back a Pandas series that we call value counts on, and that just gives us a sense of how many of each of the types. So it's going to go through and it's going to count up. There are 561 floating point columns and one object column, and same there. So, but we no longer have the this is the integer type. Refers to this data, like these are just integer counts of the data frame. We no longer have any integer columns because we dropped the subject one, and we can verify that with the info method as well. So we're just down to the floating point numbers and the labeled output. Okay, so at this point we would want to, we've looked for missing values. We've hopefully found whether there are any outliers or anything like that. But occasionally, with some of the more numeric related calculations that go into machine learning, it's going to be difficult to find good values if one of the features that you're training on goes in the range of, say, like 0 to 1,000,000, and another one goes from 0 to 1. So this is a time where you might do some feature engineering or feature scaling to amplify the signal so it's easier for the learners to find. The process of deciding which features to use is called feature selection. Feature engineering is maybe modifying it into a way that, maybe take a logarithmic transformation of the data or something to make it clearer what's going on. And then the normalization process we'll generally turn the data into normally distributed data, centered on 0 with a typical standard deviation. Many models assume a standard distribution or a normal distribution like that. So this is the kind of transformation you would do at this step. And if we look at the nature of the data that we have, there's a function called describe that will go through and calculate for each of the features the number of values, the average value, the standard deviation within that value, the minimum value, the maximum value, and then the various quartile percentiles. So 25% of the data has a value of 0.26 or less, 50% of the data has a value of 0.277 or less, 75% of the data has a value of 0.288 or less. The minimum represents the 0th percentile, nothing has less than the minimum value, and then the maximum represents the 100th percentile, nothing has more than that value. But what we see in the description of the data here is it's fairly consistent, right? The minimum and the max values and the percentiles and everything are already pretty clean. They seem like they're already normalized. So this is not something that we don't have to do this kind of transformation here as well. So that's useful. Let's just double check quickly on the test data that that's the case as well. And it looks like, again, we've got the same counts for everything. We're not missing values as we've already established. So we don't need to do much going on there. So we don't need to do it. But just to be clear and fair and help you understand the data science process a little bit better, we mention it just as something that you might have had to deal with here. All right. So this is kind of a funny way of doing this, but we're going to look at the data types, right? The last couple of data types involve the final 4 features, and then the last column is our activity column, which is the labeled output. We're going to want the ones that we're going to want to pull out the activity column. We're not going to train on this data because that's our output. That's the thing that we were trying to correlate with. So this is just kind of a funny way of saying find all the columns that are of an object type and extract those columns. For our purposes, that's just the activity column, so we don't need to worry about that, and we can simply refer to the last column as the thing that we want to train off of, or we want to train against. So now we can do a value counts of the activity column and see that, there's a fairly even distribution, roughly 1,000 samples, a little bit more lying down than walking downstairs, but they're all in the range of about 1,000. So we don't have any real skews, any strong skews in the classification. Sometimes you have very disproportionate imbalances in classification, and there are usually a variety of ways that you could address that as well. So not something that we have to deal with. There is something that we have to deal with here, though, and that's the fact that machine learning depends on math, and in this case, we have labels. And so what we have to do is we have to convert those labels into numerical values. And there's a variety of ways of doing that, but we're going to use something called a label encoder that's going to go through on the activity column and, in essence, convert them to a series of numeric values. So each label will have its own value. So in this case, we're creating the label encoder, we're iterating over all the training and test data, and we're, in essence, overwriting the existing value. So where it's an object value up above, we're going to turn it into a numeric value with the label encoder by transforming the data. So now if we take a sample of 5 values from our training activity column, you'll see that we have actually, I'm sorry, I ran that twice. I should not have. So here I'm clearing the output just to make sure that that isn't going to impact the data. I'm going to quickly rerun everything we've done so far. But we don't have to worry about that. I need to drop the column again. And that stuff is all just informational. So pull out the object feature. The problem is I ended up encoding the label multiple times, and originally it was an object and then it was not, and so that was not a good thing to do. So now if I run the sample one, I'll see that I have instead of having standing or sitting or lying down, I have a numeric value for that. And for the test data as well, making sure that we applied that, so we're good. Okay, so now we're ready to look at the interrelationship between the features. If the data is highly correlated, then we end up having this problem of a lot of noise. The signal is weak, and weak signals can still sometimes be picked up by models that are more susceptible to weak signals. We talk about the model's flexibility, and that's really a measure of how much attention does the individual data point have. So if there's a lot of noise in the data, sensitive models will pick up on that noise and think that it's meaningful, and that's not the case. So one of the things we want to do is to check the correlation between the features. As an example, if we had two columns of data and they both represented temperatures, but one was in Fahrenheit and one was in Celsius, those would be very highly correlated columns, right? Because it's essentially the same information, and both in terms of the cursive dimensionality, where we don't want too many features because it has an impact on the tendency towards overfitting, we would drop one of those columns, because in that case we have twice as much data but not twice as much information. And usually it's the information in the points and how they interrelate with each other that is the signal that we're trying to represent. So we're going to pull out our feature columns, and our feature columns are going to come from our training data, and we're going to grab all the rows and the last up to but not including the last column. So -1 just means the last thing in this case, because the columns, we're skipping the last column. Then we're going to call the correlation matrix. This is a function Pandas provides, and we're going to generate a representation of that correlation matrix that gives us a sense of what that looks like. So in essence, we're comparing each of our features against each of the other features to see how highly they correlate. And obviously that's a fairly complicated calculation. So we see that feature t-body acceleration mean x compared to t-body acceleration mean x. So in this case, we're comparing the feature against itself. Obviously that's highly correlated, but we would want to skip on the self correlation ones and look more at like how does the x and the y correlate. So that's 0.14. Correlations can also be negative. In this case, the mean x value for body acceleration and the mean z value for body acceleration are negatively correlated. But the main thing with correlations is the magnitude of the correlation. So a correlation could be very strongly positive or it could be very strongly negative. To find the highest correlation, we're going to add a new column, which is just the absolute value of the existing correlations, and look at those. So notice rather than -0.25, we have 0.25. Obviously the positive ones stay the same, but now we can compare which are the strongest correlated features and see what those look like. So in this case, we're going to sort the values based on correlation in descending order, and then we're going to run this arbitrary query that says select all the ones for which the absolute correlation column has a value greater than 0.8 and sample some of the results that are there. And we'll see that these are much, much stronger correlations, right? So the body's gyroscopic interquartile range for the x value is highly correlated with the body's acceleration. I don't know what MAD stands for. I would have to go back and look at that. But in this case, the minimum acceleration of the body when it's in a jerking motion is highly correlated with the body's acceleration and standard deviation. So notice it's negatively correlated, but it's a strong correlation.
Brian, sorry to interrupt
you.
Again.
No,
Just
no
a couple
problem.
more questions that have come through.
Sure.
So I think this is meant to read, shouldn't the label be different? How do you differentiate between them?
The labels are different. The label encoder is taking care of that for us. It's going through and it's effectively finding all the values that we have for that label. So standing, sitting, etc. And then it's just assigning instances of those to a particular numeric output. So unless I misunderstand the question, it is treating them as separate.
Brilliant, thanks for that. And just a comment that has come through, downgrade to NumPy using command pip install NumPy equals 1.19.3. I'm not quite sure what that's referring to though.
That might be a suggestion for the other attendee. If it was a mismatch, then the pip tool maybe pulled in a newer version that's incompatible, and this suggestion is something that they can run in the terminal to downgrade the NumPy library. So that's maybe something to try. Thank you if that's the shared contribution from another attendee. Was that it?
Yes, that's it for now. Yeah.
Okay. All right. So at this point, we've analyzed the data. We've looked for outliers. We've done the normalization check. We've converted the labels into numerics. So now we actually want to split up our training and test data, and we're going to use a technique called Crossfold Validation. A particular one is called Stratified Shuffle Split. I'll let you look up the documentation to see exactly what it's doing, but in this case, it's going to take our data and it's going to split it into 3 separate cuts, and each cut is going to use some amount of the data for training purposes and some amount of the data for testing purposes. And so we're going to generate the training data, and we're going to pull out the X values from the test data and look at the value counts of those. I'm sorry, validation counts of those. So here we see those numeric values. Here we see these numeric values. And again, they seem somewhat similar. So this is a process of, as you're testing models, you're going to want to validate how the configurations of the models are working, but we don't want to use our test data for that. So we're taking our training data and in essence splitting it up into additional training and test data, but we're doing so in a way that automates the splits. So if cutting the data up in one way versus another impacts the quality of the learning process, this is where we would detect that. So this talks a little bit about it, but this is a cross-validation technique that's going to give us randomized data sets that are split up, and it's used for testing whether the data splitting process is impacting our results. Okay, so then the final steps of our activity are to actually do the learning. And so we're going to use logistic regression, which again is a type of classification. And we're going to do it kind of with a straight standard logistic regression with no special configuration. We're also going to use a logistic regression that does its own cross-validation like we just did. It'll do it automatically. And then the series of parameters. I'm running a little bit behind, so I'm going to let you read through those, but the basic nature is we've got one training model up here, which is the regular logistic regression, one that's using cross-validation in the training process, like we just showed up above. So that's going to try various penalties and slice the data up multiple times, and that way we can validate which penalty gives us a better result. And so that we are evaluating our approach without actually touching our test data. So that's what's going on behind the scenes. And then a random forest classifier, which is kind of a randomized walk through the data. In this case, we're going to say generate 10 random trees of questions, and it's going to say this question splits the data set in one way, and this question splits the data set in another way. And by giving it the ability to find meaningful splits in the data, it's able to find ways of classifying them somewhat successfully as well. So what we have here are just 3 separate classification approaches, and then you can see that the results or the training process look identical, right? For each one, even though they're representing different training model learners, the fit function takes our input X data and our corresponding Y data, and then tries to fit them together, to try to find the correlation between them. And this is what, again, one of the nice things about Scikit-Learn is that it has great consistency between them, so it's easy to swap them out. So I'm going to run this step. At this point, we have trained the models, and now we are going to try to predict them. So we're going to iterate over each of our model types, and we're going to generate the results of the predictions. So in this case, we're going to make predictions with our model of our X values and append those to the lists and see what it ends up coming up with. So again, this is a fair amount of iterative code over multiple data sets. This will take a second. As you can see, the asterisk is still spinning. So it's looking through all the combinations of these for each of our 3 learners. Hopefully it'll finish shortly. It's running on a MacBook Air, so it's not a super powerful machine. So while that's going, I'll just go ahead and explain what's coming up next, and hopefully we'll get a chance to see that. So once the models have trained, and once we've done some cross-validation behind the scenes, then we want to calculate the metrics to evaluate the models. And in this case, we have a series of metrics. One is called accuracy. And accuracy is just kind of like an overall ratio of how often did you get things right. Recall is how many things were you expecting to find in a particular category that you did find. So for example, if you were trying to predict whether somebody had COVID or not, then a measure of the test would indicate if there were 10 people in the data set who did have COVID and you found all 10, then you would have all true positives and no false negatives. A false negative is a miss, right? You missed somebody who had COVID. So recall is one way of measuring that part of it. Precision is how accurate were you in your predictions, because one of the ways that a classifier could look very good is just to say, okay, everybody has COVID, right? Because on the recall metric, you will successfully identify everybody who does have COVID. You won't miss anybody. But what the precision metric is telling us is, yeah, you were wrong a lot more than you were right, because you had a lot of false positives. You said that there were people who had COVID who, in fact, did not. Okay, so good. Our results are done. And what this shows us is, for the particular data sets that we have, making predictions between the 3 different classifiers, the inputs predict the same results in all of our samples. Now, that's probably not the case everywhere, but all 3 classifiers said the predicted data come out with the same label. That's a good sign, right? That shows that even using 3 different approaches on the same data set, they learn to represent the activities successfully well enough that they all say the same thing. That's generally a pretty good sign. And this just shows you the probabilities associated with the individual elements. These are the class membership probabilities being printed out. We're showing you the first 10 rows of the 3 values there. Okay, so accuracy is the overall measure of precision and recall, right? You can see it's the ratio between true positives, true negatives, false negatives. Recall is a measure of, did you find everything you were looking for? Precision is a measure of how well did you do? And then the F1 score is the harmonic mean between these. So we're going to very quickly generate the results there. And we can see that, again, there's high consistency between the 3 results. On a precision, we have 98.4 or 98.5, 98.6, and 97.5. So each one of those models is fairly precise. We see that the recall is quite good. We see that the F1 score is good, and the accuracy is good and consistent between those. So this is a way of us evaluating the learning process, and it seems like we did a good job. The next thing that we can do is to use what's called a confusion matrix, which is a visual representation of how well it did. So in this case, again, I'll leave it as a homework assignment for you to evaluate what's going on, but we're going to generate, using the Seaborn library, what's called a heat map. And this is going to basically show us, based on the predictions, how did each model do. So it's labeling each model based on the learner, and we're saying, how often was it label 0 when we said it was label 0? And for the first logistic regression classifier, it was 422 times. So notice we never mispredicted that column. This column we mispredicted 18 times, but the vast majority of the time, 368 out of 386 total predictions, when it was a 1, we said it was a 1. When it was a 2, we said it was a 2. So these are the accurate predictions down the diagonal. Anything off the diagonal tells you where we got it wrong. And notice the models have quite a lot of similarity between them, where they're getting things wrong. So, maybe it's not surprising that a logistic regression and a logistic regression with regularization turned on would do somewhat similarly. Again, regularization is just a technique because we have so many features, we're trying to suppress the impact of the weaker signals. But also it's interesting to see that the random forest roughly has some of the same kinds of errors in there as well. But as we said, overall, we did quite a good job. So to conclude, we've just walked you through a kind of fun, modern, 21st century data set, right? Collecting data from people just based on having a phone attached to their belt throughout the day, their various activities. If they're standing, sitting, lying down, we're collecting those values. We read them in using Pandas into a data frame. We split it up into training and test data beforehand. We evaluated each of the features. For our purposes, the good news is the sensors all produced roughly the same kinds of values. We didn't see a lot of variation. We didn't have to do any feature scaling. We didn't have any missing values. So then we could move on to the codification of the label as numbers. So we used a label encoder for that. We then split out the columns that we want to train off of to compare them to the labeled output and find correlation between the inputs and the outputs through some kind of machine learning process. We also evaluated the correlation between the data sets there. Didn't do a whole lot with it, but That's just the general process that you'll go through. And then we picked 3 separate learners, trained them with different parameters, and then evaluated each of the learners and their predicted results against each other, and saw that we had high consistency between them. So overall, we would say this was a quite successful activity, and we should feel fairly comfortable that given the strength of the signal in the gyroscopic readings, correlating nicely with the activities that the people were doing, we would have confidence that we could take those models and fold them back into the phones and keep track of people's activities throughout the day. So now we would know, how often are you walking? How often do you walk up steps? And you don't have to type that information in itself. It can just naturally observe what you're doing, and as we can see, have a pretty clear indication of what it is that you're doing. So I hope you enjoyed this. Are there any other questions?
No more questions have come through.
Okay. So again, my email address is my first name dot my last name at Gmail. If you had a question about the thing and you want some help setting up, please drop me a line. My name again is Brian Sletton, and I hope you enjoyed this. Please explore the Reactor GitHub repository. There's a lot of great materials there. A lot of it is self-describing, and you can work your way through it. But check the schedule and come back and attend some other sessions. This is remarkable that in the time of something like a global pandemic, we can still get together and talk about things like this. So I hope you've found it instructive and useful and interesting, and it encourages you to dig a little bit deeper. So thank you very much. Stay safe and have a good day.